So, hello everyone. Today we will be starting week 7, that is design and analysis of biological reactor. So, in this module mostly we will be discussing different type of bioreactor. First we will start with ideal bioreactor, particularly this batch, fed batch and continuous mode of operation. So, today we will be discussing this ideal reactor operations in the batch, fed batch and continuous mode. If you quickly revisit the last week, we discussed structured kinetic model, and here we discuss why we need structured kinetic model as compared to the unstructured one, and then we discuss compartmental models, Williams and Ramakrishna's compartmental model. Then we discuss model based on the cellular energetics and metabolism like transcription and translation. Then further we compare this unstructured and structured models. Followed by that we discuss similar thing for the product formation. In the product formation we discuss chemically structured product formation kinetic models. Then further we discuss genetically structured model, and for the molds and fungus we discuss filamentous microbes models. And in this today's lecture we are going to discuss the first operation, that is the batch operation. Now in the batch operation we can have cell culture or we can have enzyme reactions. We will be discussing both one after other. So what is ideal reactor operation? It provides a theoretical framework for designing and analyzing chemical and biochemical reactor under simplified, that is called ideal conditions. So, by assuming the perfect mixing or plug flow, constant volume, uniform properties such as temperature, composition, density, viscosity, engineers can derive clear relationship between reactor size, volume, residence time, T, conversion, percentage conversion and percentage productivity. So, these are the important parameters for bioprocess engineering: reactor volume, residence time, conversion and productivity. And these idealized model, particularly batch reactor, continuous stir tank reactor and plug flow reactor, they serve as benchmark for comparing real system and further guiding for the scale up decisions. In addition to batch and continuous, there is another mode that is called fed batch mode, that also we will be discussing. Fed batch. Now, what is the objective to study this ideal reactor operation? First, we can establish material balance to relate reactor volume, flow rate and reaction rates. So, material balance, inlet, outlet, generation and utilization, that should be equals to rate of accumulation. It helps us to derive analytical expression for the conversion at a function of time or reactor volume. And then we can compare different reactor types on the basis of conversion, productivity and sensitivity to operating conditions. So, actually it provides a basis for more advanced modeling that incorporate non-ideal behavior and dynamic phenomena. So, in this week we will be mostly discussing the ideal behavior. Now, next, what are different modes of operation? Batch, fed batch and continuous. One more is the plug flow. Batch means you just see there is a no inlet, no outlet. In the fed batch there is inlet, but there is no outlet here, and in the continuous mode both the inlet as well as outlet is there. So, this is the major difference between batch, fed batch and continuous. Batch is a, you can say this is a closed system. So, there is no inlet of mass, In the fed batch, intermittently feeding is done, but there is no outlet, and in the continuous, there is a continuous supply and continuous outlet. So, it basically operates at steady state. Now, this different mode of operation, they affect the reactor performance, particularly the conversion of biomass, substrate and product, as well as the time required. So, those particularly we will be seeing the kinetics in terms of biomass, substrate, product as well as the time. And the last one is the plug flow reactors. So, it says there is no lateral mixing in this case. It is also a continuous mode, but there is no lateral mixing. Now, when we are operating these type of bioreactors, we need the biological agent that can be a free cell or free enzyme, immobilized cell or the immobilized enzyme. So, we will be considering these biological component while discussing the kinetics of these modes of operation. So, first we will start with the batch operation. It operates in a closed system. So, we feed all the reactant at the start, further there is no feeding. This is very common for the production of enzymes and cell culture, and what is important here, the vessels contain uniform, particularly this constant volume if there is no leakage or evaporation. So, when we are deriving expression for the rate, we can always consider the constant volume for the batch culture. Now, as we discussed, first we will be doing the mass balance. So, we remember the mass balance we have discussed earlier also. There is a mass of inlet minus outlet plus generation minus utilization, this equals the accumulation. So, we will be following the same here. The mass of entering biomass in the bioreactor 0, mass of the generation of bioreactor Rx into V, mass of the cell leaving the bioreactor 0, mass of the consumption or utilization 0, and rate of accumulation dxv upon dt. So, we will end up with dxv upon dt equals Rx to V. So, as we are using the constant volume, V can also be cancelled out. So, and for Rx for time being, let us consider Rx as mu x. So, this becomes dx upon dt equals to mu x, and if you integrate, we will get xf as x naught e to the power mu into t. So, from here we can derive what will be the batch time Tb. Tb will be equals to 1 upon mu ln xf upon x naught, and many times when we calculate this batch time, we say mu equals to mu max. So, here we consider there is no cell death, but in actual there will be cell death. So, how to incorporate the cell death? So, we say dxv upon dt equal to mu x v minus kd into x into v. Kd is the cell death rate constant, or you can say R equals mu minus kd into x. Again, if you can integrate this expression, you will get xf equals x naught e to the power mu minus kd into t, and from here if we calculate the batch time, this becomes 1 upon mu max minus kd ln xf minus x naught. So, if you know what is the initial biomass, final biomass, we can calculate the batch time, or if you know the batch time, we should be able to calculate the final biomass concentration. Now batch operation, balance for the substrate. Again, but substrate inlet 0, substrate generation 0, substrate outlet 0. Now here there is a consumption of substrate, that we are writing RS into V, and this rate of accumulation of substrate. So it becomes dSV upon dt equals minus RS into V. Now it is very interesting to consider what is RS, rate of substrate utilization. So we are assuming the substrate is utilized for, substrate is going for the biomass, substrate is also going for the product formation if any, in addition it is also going for the maintenance. So RS is written as, RS is, mu is the rate of, mu x is the rate of biomass divided by what is the yield of biomass from the substrate, y x upon s. Similarly, Qp is the rate of product formation into x divided by y p upon s. Similarly, ms maintenance coefficient into x. So this is RS, rate of substrate utilization. If you put the value of RS over here, we are writing here into x. So it becomes ds upon dt equals minus 1 upon y x upon s mu minus Qp upon y p by s plus ms. And what is x? X we discussed, derived in the last slide. X is x naught e to the power mu into t. So x is now replaced by x naught into e to the power mu t. Now we replace mu as mu max. So whatever mu is there, mu will be replaced by mu max here. And if you consider this term as constant, we can quickly integrate this expression and we will get Tb batch time as 1 upon mu max ln under bracket, all the term will come under bracket 1 plus S naught minus SF divided by RS term will be there. You can quickly write here 1 upon y x by s plus Qp upon mu max y p by s plus ms divided by mu max, this whole multiplied with x naught. Now further you can assume if the product formation is not there, this term can be 0, and if you remove the maintenance part as well, then this term can also be 0. So we will end up with Tb as 1 upon mu max ln 1 plus S naught minus SF divided by 1 upon y x upon s into x naught, or y will go up. So what we are getting here is 1 upon mu max ln 1 plus y x upon s naught minus SF divided by x naught. And if you remember, what is y x upon s is x f minus x naught divided by s naught minus SF. So what we can do, we can replace this y x upon s, if you replace it here, then s naught minus SF term will be cancelled out. So here we will end up with 1 plus xf minus x naught divided by x naught, and this will be, this x naught will be cancelled out. So we will be ending up with xf upon x naught. So this equation will be further reduced to 1 upon mu max ln xf upon x naught. If you remember this, this is the same expression we derived from the biomass balance. When we did the biomass balance, we end up with the same expression. TB is 1 upon mu max ln xf upon x naught. So, what it says, we can interconvert between the substrate biomass as well as for the product. Now, next quickly we will see the product, the mass balance for the product. Inlet is 0 for the product. There is a generation of the product. So, we say Rp into V. Outlet is 0, consumption is 0, and this is the rate of product. So, it says dPV upon dt equals Rp into V, and Rp we write Qp into X, specific product formation rate into biomass. So, this becomes dP, V is constant, so can be cancelled out, dt equals Qp into X, and X can be replaced by X naught e to the power mu t. So, if we quickly integrate it and we assume the bioreactor operates as mu equals mu max. So, we will get TB batch time as 1 upon mu max ln 1 plus mu max upon x naught Qp. This will be Pf minus P naught. So, this is very simple. So, we can do the calculate the batch time based on the substrate, biomass and product balance, and in all the cases the results will be this comparable. Now, we will see one example here, that it is a genetically engineered strain equally is used to produce human protein. A batch culture is started by inoculating 12 gram into 100 liter bioreactor. So, it says x naught equals 0.12 gram per liter containing 10 gram per liter of glucose. S naught equals 10 gram per liter. The maximum specific growth rate mu max is 0.9 hour inverse, and biomass yield y x upon s is 0.57. Now, first you have to find the time required to reach the stationary phase. It means you have to calculate the batch time. Quickly you can calculate, if you remember, TB equals 1 upon mu max ln, if I write in terms of biomass, so this will be ln xf upon x naught, but here xf is not given here. So, xf is not given. So, how we can find xf? We can find xf from y. So, what is given here is y x upon s, this equals xf minus x naught divided by s naught minus s, and if I rearrange this, so this becomes xf as x naught plus y x upon s, s naught minus s. So, for time being you assume the complete utilization of substrate s as 0. So, we will get the value of xf as 5.87 gram per liter, and once xf is known we can quickly calculate the batch time, that will be 4.32 hour. Now, part B, what it says, what will be the final biomass concentration xf if fermentation is stopped after only 70% of substrate is consumed. So, it says now here we assumed S as 0, we have to now assume in case of part B S as 70% is utilized of the 10, so 7 gram per liter is utilized, we are left with 3 gram per liter. Now, what you have to calculate, using the same expression we can calculate the what will be the xf here. So, it will be x naught plus y x upon s, s naught minus s naught is 10, s is 3, y is 0.575. So, we will get s as 4.215. So, that is obviously gram per liter. So, it is lesser than the 5.87. And here again you can calculate what will be the batch time. So, you can quickly calculate the batch time. So, for the part A, for the complete utilization, the batch time was 4.32 hours, and if you calculate the batch time for part B, so you can calculate batch time for part B based on the, let us say, substrate balance. TB is 1 upon mu max 1 plus y x upon s x naught s naught minus sf, and this you will get batch time now 3.94 hours. So, the batch time is also less as compared to the part A. Now, you can back calculate the biomass. How you are going to back calculate the biomass? For part B, you can back calculate the biomass as x as x naught e to the power mu into TB. The batch time we calculated 3.94, mu is given, x naught is known, again x will get the same answer 4.15 gram per liter. So, what it says, you can do this mass balance using different equations what we discussed based on biomass, substrate or product, and at the end you will be getting the similar answers. Now, we will be discussing the batch operation using the free enzyme systems. So, what we are replacing here is the biomass is now being replaced with the enzyme. So, the kinetics will change. So, earlier we are having the Rx, now it will be RSE, since we are using now the enzyme kinetics. Again, what is the mass of substrate in the batch culture? No inlet, 0. Mass of generation in the reaction is 0, there is no generation of substrate. Mass going out is 0 in the batch culture. This is the rate of utilization of substrate, RSE into V, that equals plus rate of accumulation. So, it becomes dSV upon dt equals minus RSE into V. V can be cancelled out, we are assuming constant volume, and what we are assuming, this enzymatic reaction is following Michaelis-Menten kinetics. So, this become RSE equals V max S upon Km plus S. So, this becomes ds upon dt equals minus V max S upon Km plus S. We can quickly integrate at t equal to 0, S equals S naught, and t is equal to TB, S equals to SF. So, if you integrate it, we will be getting TB as Km upon V max ln S naught upon SF plus S naught upon SF divided by V max. So, in the case of enzymatic kinetics, if the Km and V max is known, we should be able to calculate the batch time required. Further, when we are dealing with the enzymatic system, it is important to understand the enzymes are susceptible to the external environment, particularly to the temperature, pH, ionic strength. So, with time enzyme may get degraded. So, if you remember the Michaelis-Menten equation when we discussed, V equals V max S upon Km plus S. What is V max? V max is K2 into E naught. So, basically E naught is decreasing. So, V max changes. So, V max becomes V max 0 into e to the power minus kd into t. Or you say how you are going to write, if you remember, E naught becomes E E becomes rather E naught becomes E becomes E naught into e to the power minus k d into t. So, we are assuming here this active enzyme is converted to the deactivated form and rate constant is k d. We are assuming the first order kinetics here. Now, what is going to change here? And we will be writing the kinetic equation, it will be ds upon dt equals V max will be replaced by V max 0 e to the power minus k d into t into s divided by k m plus s. This is again simple integration, we can quickly integrate it. So, we will be getting this k m plus s divided by s will come here, this here ds. The boundary condition is s naught to sf, this equals 0 to t, V max initial value into e to the power minus k dt into dt. So, if we integrate it, we will be getting very simple equation and we can find the value of batch time. So, batch time will be coming as minus 1 upon k d ln 1 minus k d k m upon V max ln s naught upon s plus s naught minus sf upon V naught max. Now, here again if k d is 0, this equation will be converted back to the same equation which we discussed in the last slide. Now, we will have a quick example based on this. It says an enzyme is used to produce a compound for manufacturing of a lotion and V max is given as 2.5 millimole per meter cube per second. Km is 8.9 millimole, S naught is 12 millimole. They have to calculate the batch time TB, you have to calculate the TB for 80% conversion. So, S will be 12 into 0 0.2, 2.4 millimole. So, this we can convert into the millimole per hour. So, what you have to do, this will be 2.5 meter cube into 1 upon 1000 into liter. The second will be this 3600. So, we will be having 9 millimole per hour. Now, TB we can directly apply the equation which we discussed for the simple enzyme kinetics, because the rate of deactivation k d is not given here. So, we can assume k d as 0. So, it says this will be TB as k m upon V max ln S naught upon SF plus S naught minus SF divided by V max. All the parameters are known. If you put this value, you will get the TB as 2.66 hour. So, batch time will be 2.66 hour. Further, what happened, this if it is immobilized enzyme. So, in that case again you are going to apply the similar kinetics. It becomes ds upon dt equals minus V max S upon Km plus S, and in addition we are going to apply an effectiveness factor, total effectiveness factor of the enzyme immobilization. If you remember this applied enzyme catalysis, then total effectiveness factor becomes external effectiveness factor due to external mass transfer into effectiveness factor due to internal mass transfer. So, because of the mass transfer limitation, we have already discussed how to calculate the effectiveness factor, and final effectiveness factor need to be multiplied here, and rest of the integration what we have discussed for the free enzyme, we have to repeat the same for this case as well. Now, we can quickly see how we see the total batch time. So, what we have calculated is we have only calculated TB here, but total batch time indicates TP needed to clean, sterilize and prepare the bioreactor. TP plus TI, there will be lag time as well in the batch, which is required for the cell to get acquainted with the new environment. It may be the media, it may be the temperature, it may be the operating condition, and once batch is done, there is also time required to harvest this THP. So, total batch time becomes TB batch time what we calculated plus downtime, and downtime includes this cleaning time plus lag time plus harvest time. So, whatever we have calculated TB, that need to be added with the total downtime to get a complete idea of time required for a batch cycle. So, with this I will stop here. So, today we discussed the batch culture, we did the mass balance for the biomass, substrate as well as the product for two systems, first for the cell culture and second with the enzyme reaction. Thank you so much.